All right, it's time to start. For those of you who were excited to come here and do some computer work and haven't been paying attention, boy, do I have some bad news for you. There's about 30 more minutes of lecture before we get to that, but there is some computer stuff I want to do at the end, so I'm going to leave some time. But there was just too much content this week, and I didn't want to try and cram it all in a quite limited space. So today, we talked about the idea of conservative vector fields, fields for which you could construct a potential, a scalar potential, for which you can write that the gradient of that scalar potential is the field. Such fields have very useful properties because their line integral is path independent. It doesn't care how you get somewhere as long as you do, which is to say the integral value depends only on its endpoints. We then generalized this a little bit, and we said, well, actually, it turns out that the test to determine whether such a scalar potential exists comes from the curl. And in fact, if we move back and think about the integral of the curl over an area, then we get a nice little relationship between the 2D integral over an area and the 1D line integral over its boundary. And of course, you can see that our stuff about the scalar vector field, the scalar potential field, falls out of this by saying, well, what would this be if the curl was 0? It would be 0, and you get the result back. So everything we did in the first half is kind of a consequence of Green's theorem, but that's not generally the nicest way to introduce it. So then we proved Green's theorem and said, okay, so the integral of the curl over a region is equal to the integral of its I'll say differential form, but the integral of the work done by the field around the boundary. So the projection of the field onto the tangent of the boundary integrated up. Because remember, what is a line integral but taking the projection of the field onto the boundary and adding all those little bits up? So it turns out that both directions of this theorem can make your life easier depending on context. Typically, it's easier to go, well, I've got some line integral and I can just work out the curl and integrate up the area, because it is easier to get the curl. It's just taking derivatives. But sometimes it's useful the other way as well, and that's going to take us in a bit of an interesting direction. So we did an example. Where I said, here's this horrible line integral that you don't want to do, but maybe this is a little bit easier if you work out the curl of the field and just integrate that over the rectangle. And it is easier, although I did get it wrong, so that number is probably not minus 9 over 2. I will fix that before I upload. Okay, but maybe we're lucky. Maybe we can go the other way. Doing this the other way is less obvious, but it is really nice when it works. That doesn't sound encouraging, but there is a good reason to want to do this. So just let me pull up my page. All right. So write a line integral for the area of a simply connected region A. That's it. That's the whole example. So we know from week 3 that if I have some region A, then the double integral of 1 dx dy is its area. You can put a 1 there if you want, but of course, if we don't put anything there, we interpret that as being of 1. Okay. Well, what I'm going to do is I'm going to say, a thing I know about the number 1 is that I can write it as a half plus a half. Good. I'm seeing nodding. I'm glad that everybody agrees with this. And what I'm going to say is, wouldn't it be nice if this was in fact py minus qx dx dy? That would be convenient. Well, let's see if we can't construct ourselves a p and a q. So py is equal to a half. So p, I'm just going to say, is equal to y over 2, plus some constant, but maybe even some constant depending on x. But we did a lot of work with that today, and here we're just going to trust that this works out. Qx is equal to minus a half, because remember, we want this to be minus qx. So q is equal to minus x over 2. So py minus qx is equal to y over 2 minus x over 2. So maybe instead of doing this incredibly easy integral, well, maybe A is a bit complicated, maybe it's not totally easy. Well, it turns out that the area is equal to the integral around the boundary of A, P dx plus Q dy, which is equal to a half integral around the boundary of A of y dx minus x dy. And in fact, that is true. If you integrate around any shape, this quantity, then you will get its area. So that's a neat little example. We're going to push this idea a bit further, but there's a question. Because that is Green's theorem. Oh, off by a minus sign? Am I off by a minus sign? But I didn't drop one. So I've cancelled out my mistake. Is that what we're saying? Let's do this right. Let's call it qx minus py. Wait, let's use the qx minus py. So qx has to be a half, and q has to be x over 2. And py has to be minus a half, so p has to be minus y over 2. So qx minus py equals x over 2 minus y over 2. If this doesn't work, I can clean this up later. So what we should get is, you know what, there's a mistake there, but we'll fish it up later. I don't have time to fix this up on the fly. It is a bad idea. Check the notes for the correct version. It's just a bad idea. We want to push this a little bit further. Is there a beeping noise? Sorry, that is killing me. Nope.
Yeah, it's not in its... No, it's in the phone on the table. The black one. That's...
Ah. All right. Boy, fixing an algebra mistake that is very well hidden while having that beeping going on was going to drive me to an early grave. And I am doing my best to get there already. Suppose we have a region A with a boundary parameterized by x of t and y of t. Okay, let's think about this properly. This thing has a tangent vector and a normal vector. The tangent vector, which we know is... I'm going to unplug this phone.
You think it's the phone? I don't think...
I don't know, but I'm going to tell...
Yeah, it's not recording. It's not recording.
Oh, no, the light doesn't work. That's well known. What about now? Didn't like the weight of my laptop. All right. Now we are in business. Okay, so we have a tangent vector and we have a normal vector. The normal vector, n of t, so our tangent, let's just enjoy the not beeping for a moment, is x dashed of t, y dashed of t. And the outward pointing normal, an outward pointing normal, is y dashed of t minus x dashed of t. Now, we are eventually going to want that to be a unit vector, but we'll worry about that down the track. So the area, and look, this formula for the area is true. So I will fix up the previous slide to be consistent with what's written here, which is a half the integral partial a of x dy minus y dx. That is a true fact, which is equal to a half of the integral in the positively oriented direction of x of t, y of t, dotted with y dashed of t minus x dashed of t, dt. Okay, so that, I've just rewritten this integral in this form. So we get xy dashed minus x dashed y. So here's our y dashed, here's our x dashed, once we write it in differential form, which we are going to define as being, so this is a definition, a half times the integral around the boundary of our field projected onto the normal vector. And I'm going to say a unit normal vector, and I'm going to say a length operator, a length element. And we are going to define these more carefully on the next page. But I'm suggesting that this area is the projection of the field not onto the tangent vector, but onto the normal vector. Happily, Green's theorem can tell us something about this as well, and a very important thing. So here, what I've written is the unit normal vector. It's what you would expect. I calculated out the elements of the normal vector, and then I divided by its magnitude. A normal vector really is a measure of a direction without a magnitude, in some sense. Its magnitude is 1, which is multiplicative identity. What we're saying is the direction of the normal vector is the thing that's important for this calculation. And ds is the arc length element. So ds, you'll remember when we did arc length integrals, represented the unit arc length. So parameterizing this boundary in terms of its arc length. And that parameterization we derived, and we found that in this case it would be x dash squared plus y dash squared dt. Can someone close to the door close the door, please? We can't have the saw noise. We figured this out earlier in the semester. No? Okay, that's fine.
They did try.
Yeah, no, I know. It's just not going to work. Okay. All right, so let's put these bits in. So this tells me that what I'm actually calculating is y dashed minus x dashed over the square root of x dash squared plus y dash squared. Great. Square root x dash squared plus y dash squared dt. Kick out the doorstop. All right. So this is in fact what we mean when we write a half integral partial a f dot n ds. So this is a notation you will see a lot, and what it really means is the unit normal arc length element. Okay, so this integral has a name. It's called the flux integral. So the line integral measured the projection of the field onto the tangent vector. The flux integral measures the projection of the field onto the normal vector, acting perpendicular to our curve. It describes the flux of f across partial A. Flux really does come from the word for flow through. We really mean the projection of the field onto the normal direction, but all of these things, particularly in vector calculus, come from a historical use that got kind of generalized into more strict mathematical ideas, and flux is a concept that stuck around. So flux is the action of the field perpendicular to the curve. Yes? It could be flux along a line, but we're going to focus on boundary here because we're about to use Green's function. But yes, a flux integral can be along a curve. It doesn't have to be a closed curve. Okay, so this is a flux integral. Flux integrals integrate the projection of f onto the outward pointing normal. So actually, you probably do want it to be on a curve because it needs to have an outward normal for it to make sense. You'll see it on curves anyway. Good question. I'll come up with an answer to that, but I don't have it off the top of my head just because you normally think about these things on closed curves. So the normal should be outward for this to be a sensible concept. The flux integral integrates the projection of f onto the outward pointing normal of some curve. And to measure this, well, look, I mean, if we're acting perpendicular to this circle at least, you might start to think that the divergence is going to be relevant here. And this would be true. So maybe we should calculate the divergence and see where this takes us. So to measure this, we're going to want to consider the divergence of the vector field. I spent the last hour talking about curl. Now we're talking about a different operation, divergence. And as a reminder, the divergence of my field f is equal to grad dot f, which is equal to mx plus ny. So remember, the curl would have been ny minus mx, or possibly the minus of that. So it sort of makes sense, at least in a circle, that stuff acting in the direction of the circle was given by the circulation, its curl, and the stuff acting perpendicular to the circle comes from the divergence, its spread, and we're going to show that that is true more generally. So this picture is not a proof because, of course, not all curves are circles. But now we have an extra tool in our back pocket, which is Green's theorem, and we're going to make use of it. So what is the flux acting in the normal direction? We take our vector field, mn, and we project it in the normal direction, y dashed, x dashed. I'm just going to assume that this is a unit vector to make our life easier. Give me a sec. So we are going to say that this is, in its differential form, m dy minus n dx, or, if you like, minus n dx plus m dy. So we're just using not the unit normal vector here, but just the regular old normal vector we wrote down before. That's fine because projections are a direction anyway. So if we want to integrate this around the boundary partial d of minus n dx plus m dy, and we know that if we wanted to write that in that form from before, this would be, in terms of the normal vector, we would write f dot n hat parameterized in terms of arc length s. So this is in dx dy. If we wrote it in ds, we would need the normal vector. Technical point, not that important, but just wanted to get ahead of that. That's not a definition. We've already defined it. Is equal to, from Green's theorem, okay, so Green's theorem tells us that it should be the second thing, derivative with respect to x, minus the first thing, derivative with respect to y, dx dy. From Green's theorem. Green's theorem. I had to pick a color. But that is nothing more than the integral of d, mx plus ny, dx dy, which is, of course, the integral of grad dot f over the area. This is a completely equivalent statement to Green's theorem. And it is, in fact, often called the normal or flux form of Green's theorem. So what you'll notice if you went to the sample exam resource sheet that I gave you, both forms are listed. These are seen as two sides of the same coin, one acting in the direction of the tangent, one acting in the direction of the normal. One looks at the curl, one looks at the divergence, but these things all come out the same way. And this is a particularly nice thing for understanding what's happening across surfaces, because it tells us that the flux across a surface, which is to say the stuff passing through the surface, is equal to the integral of the divergence of f over d. So let's think about what that means. If this has no divergence, if the interior is divergence free, then everything coming in has to be balanced by something leaving. But if the interior is not divergence 3, maybe we have a little source here where it's spitting stuff out. Maybe we have a sink here where stuff is going in. Then stuff is being created or destroyed inside the region, which means that, say I was only creating stuff, then more stuff would have to be leaving the region than coming in. So the divergence is kind of telling you, in a sense, how much stuff is being created or destroyed inside our surface. So it makes sense that if the amount of stuff is conserved, and conservative quantities have come up a lot today, then the amount that's entering has to be equal to the amount that's leaving. So the flow through the boundary is equal to stuff. By stuff, I mean the integral of the quantity, stuff created minus stuff destroyed. It shouldn't shock you to know that this theorem comes up a lot in conservation arguments, mathematical and physical, because it is often very, very easy to characterize the behavior of a system in terms of its conservations, and every conservation is telling you about the stuff inside a region that's being created and destroyed. So if you want to know about the flux over the boundary of that region, the conservation law immediately tells you which ones should be 0 and which ones shouldn't, and therefore what this integral should do. So this is a very, very powerful thing. A classic example, if this was, say, a fluid flow problem. Maybe this is me sticking a hose in and turning it on. And maybe this is a little drain that's pulling it out. If the amount I'm sticking in through the hose pipe is equal to the amount that's being drained out the drain, then the only change, the total amount of stuff is conserved, and all of the stuff coming in has to be cancelled by all of the stuff coming out. Otherwise, my region will explode. If mass is conserved, which is what happens in fluid flow, it's the first of the Navier-Stokes equations, then you would expect that the amount of stuff flowing in is equal to the amount of stuff flowing out. So this is an important idea that has a lot of implications in PDE theory. So these, not red, are divergence not being 0. So that's nice. Okay, so what's the take home about this? And don't think this is the last slide, by the way. The important take home is that if we have a 2D region, it has a tangent vector and a normal vector, then there is one theorem that we can write in two different ways. There is Green's theorem, and we haven't written it like this before. The form we wrote about Green's theorem was just the line integral, but actually the line integral is nothing but the projection onto the unit tangent vector under an arc length parameterization. Exactly the same thing, which we know is equal to the integral around the boundary of p dx plus q dy is equal to the double integral of py minus qx dx dy, which I don't remember, or the curl of f, which I do remember. You can remember what you wish to remember. Okay, so the normal form is the same thing, except now this is a little curly, minus q dx plus p dy, but this thing is often a little more physically insightful, px plus qy dx dy, which I do remember because it's hard to forget what the divergence is, but easy enough to just remind yourself that it's this. This is the curl, and this is the divergence. The extension of this into 3 dimensions is not totally trivial. We will do this next week. It even has a different name. So Green's theorem you should think of as being an R2 theorem. We will talk about some R3 next week. Yep. It is... Yeah. There will be a point where I get this right, but today is not that point. Okay, Green's theorem, correctly. Okay, so there are a few more things to do about this. We aren't finished, but this is an important take-home. This is the first of the 3 big vector calculus theorems that we will learn. Green's theorem, Stokes' theorem, and the divergence theorem. Green's theorem is a theorem that takes a 2-dimensional integral over a region and relates it to a one-dimensional integral over the boundary of that region. Remember, and I've said this before, and I will say it again, fundamental theorem of calculus type theorems take an integral over some n-dimensional domain and reduce it to some kind of integral or sum over an n-1 dimensional boundary to that region. So this has a bit of the smell of the fundamental theorem of calculus about it. But curl and divergence, I mean, they're both kind of differential operators. So maybe things are a little more complicated. We'll put this aside for now and untangle that next week. For now, I want to talk about divergence-free flows. We know that if a flow has no curl, it has a scalar potential. What does it mean if a flow has no divergence? Well, we've said whatever flows into a region must flow out. If there's no divergence, then nothing is being created, nothing is being destroyed. The integral over the boundary of that region has to be 0 from this theorem, because if the divergence is 0, then the integral of the projection of the field onto the normal vector is 0, so the total amount of stuff leaving is equal to the total amount of stuff entering. The flux is 0. Okay, so let's untangle that and come up with something quite nice. So we have our vector field f, and we know the divergence is 0, which means that mx plus ny is equal to 0, which means that mx is equal to my minus ny. So there is a conservative vector field here, but it's not f. So minus nm is a conservative vector field. Minus nm, that's got to mean something, and it does. Minus nm is a conservative vector field. That means there is a potential, and we're going to call this potential g. And that potential satisfies minus n is equal to gx, and m is equal to gy. And this has a name, and a slightly different name to distinguish it from the scalar potentials we learned about fields divergent, about curl-free fields, which is called a stream function. And again, this is an idea which was sort of developed in application before the theory kind of nailed it down, which is why there's a lot of fluidy type words here, because basically a lot of this was invented by fluid dynamicists, and then sort of the mathematicians, the theoretical mathematicians, kind of hung all the theory on it. Contour lines of G are particle paths in the flow field. If I have some flow field and it looks like this, then the line of constant G will go like this. If I just drop a cork in the river and let it flow, that is the flow it will take in the field. And the reason is contour lines satisfy G constant, so the gradient of G, and remember the gradient of G corresponds to this vector field, points perpendicular to contours of F. We'll show that. F dotted with grad of G is equal to Mn dotted with grad of G was minus Nm is equal to Mn minus Nm, which is 0. So my field F is orthogonal to grad G, which means it acts in the direction of the level sets of G. So the contour G constant, i.e. the level sets. Because remember, grad G, the gradient operator, acts orthogonally to the level sets of G. So if F is orthogonal to grad of G, that means that F must follow the level sets of G itself. If you have a field and you drop a cork in and you watch that cork travel, then you will see the path that it will follow because it will be traced out by this stream function if your field is divergence-free. So that's quite nice. We now know what happens if a field is curl-free, and we know what happens if a field is divergence-free. And let me tell you, there is an incredibly important class of fields which are both curl-free, conservative, and divergence-free. And here is where stuff gets important. So if you are conservative, you're curl-free, then F is equal to grad of F. There exists some F where this is true. And if you're divergence-free, then the divergence of your field is equal to 0. And if you put those two things together, if I take the first line and substitute it into the second line, I get grad of grad f is equal to 0, which tells me that fxx plus fyy is equal to 0. This thing is called the Laplacian operator. We also write that sometimes as upward triangle of f is 0, or grad squared f is equal to 0, and this is called the Laplacian operator. Laplacian. And this is really, really important. This is maybe the most important PDE there is. You'll see it again before the semester is out. I just wrote the lecture on it. If f is convergent, conservative and divergence-free, it satisfies Laplace's equation. Laplace's equation is the most important PDE. It's well understood. It tells us that everything comes from the boundary, but that's not all that happens here. So now we've realized that fields that are divergence-free and curl-free actually correspond to solutions of Laplace's equation. So now we're talking about solutions to Laplace's equation. F is divergence-free, which means it has a stream function. So we don't just have f, we also have g. And remember, f wants to act orthogonally to g. So somehow we have a g, and we have an f that gives us a field, and these things are orthogonal to each other. If we put all of this together, then you'll remember our stream function was defined this way. So let's take this and copy it onto our new page. So we have gx. I'm going to write minus gx here equals n, which was fy. And we have gy is equal to m, which was fx. Earlier today, I got asked whether the Cauchy-Riemann equations would be making an appearance. These are a very famous set of equations known as the Cauchy-Riemann equations. This is the Cauchy-Riemann equations. And let's just remind ourselves where these came from. This was minus n equals gx, and this was m equals gy. The Cauchy-Riemann equations are the gap between the bridge between vector calculus and complex analysis. Because the Cauchy-Riemann equations, any function you write down of a complex variable, x plus iy, these are satisfied when you write it in a certain way. So if I say I have z equals x plus iy, and I have some function of a complex variable w of z, which I'm going to write as f of xy plus I g of xy. Any function w of z that you might want to write down, if you can break it up, when you break it up in this way as x and y, satisfies these equations. So any function of a complex variable satisfies Laplace's equation. And any solution of Laplace's equation is a curl-free, divergence-free vector field. And now we have a pathway from vector calculus through to complex analysis. And in complex analysis, you do a lot of these vector calculus ideas where your real part is your x and your imaginary part is your y. And you have a bit of extra structure given to you by the complex numbers, which allows you to do some incredibly powerful things. Complex analysis is fantastic. But how does it tie into what I was just going on about to do with potentials? Remember I mentioned the complex potential of a function. So this is quite nice, because any f plus ig is a complex potential, which stores information both about the scalar potential f and the stream function g. So lines where f is constant are called equipotentials. And that f is the exact f you need to get the field underlying everything. And any line where g is constant are called streamlines. Which means that any function of a complex variable describes a flow with equipotentials and streamlines. As a nice little example, say I want to consider I have W of z equals z. Nice, easy. So W of z equals x plus iy. X and y are going to be real, so I'm going to call this f of x, which is a nice simple form, plus I times by g of xy. Okay, so lines where f of x are constant are lines where x is constant. So here are my level curves of f. My stream function, my potential function. And here, level curves of g, which is y, so lines of constant y, are my streamlines. Streamlines. And in fact, what I've described here is a flow that corresponds to a vector field that just pushes the cork to the right. You move in the direction of increasing f. So this describes horizontal free stream flow. And in fact, before we had computers, this is basically how we did fluid dynamics. Like now we have more complicated tools. But this describes exactly that. And you can sort of figure out that what we're talking about is a flow with no viscosity, no circulation. But basically, you have a whole complicated flow structure encoded in one complex number. This is incredibly powerful. Turning complicated problems into simple representations is an incredibly powerful thing that mathematicians try and do. I want to stress, though, this is sort of the end of the theory of today, but if you only get to here, you are probably in very good shape. However, if you want to go on and do higher-level complex analysis, higher-level PDEs, this is really good stuff to have seen before. So we want you to see it, but like if this was sort of pushing the envelope a little bit as to how tough we want this to be. If this is a bit much for you, don't panic. You will cover this again before you ever need to use it, and probably not in 15 minutes. Question? Yes, but it turns out curl zero, divergent zero fields are very, very common. They're very, very important and are often constructed to be so. For instance, all of electromagnetics, all of inviscid fluid dynamics can be constructed in terms of those fields. Yep, because you want a complex potential to exist. Okay, take 2 minutes while I set up my computer, and then we're going to look at some vector fields. What's the best thing of all time? Sorry? Oh, I know.
And 2 weeks later, he was like,
Complex potentials are the best thing in life. Your friend is right.
oh, gross. Maths? Okay. I can't say that. Half my friends about it. Real. I'm going to make money.
Okay, I've got my computer set up. If you have this open in front of you, I'm skipping the first section, which is just about how to deal with matrices and vectors. You probably shouldn't skip that, but, you know, we're almost done, and I want to focus on the interesting stuff. Mathematica was made for this. This is what it is for. Visualizing vector fields is hard, but as you can see, looking at a vector field kind of tells you everything that's going on. A lot of the stuff that we talked about using complicated proofs, using difficult diagrams, is really obvious when you actually look at the vector fields. So let's look at a vector field. F of xy equals minus yx, a field we know well. Now we know that this thing is going to be curl-free, divergence-free. curl-free, divergence-free. And we plot it, and you can see this is our field. Now, this is a bit hard to interpret. So what it does is it throws down an arrow, which is just direction, and the magnitude of the vector is indicated by the color. Small vectors, dark, large vectors, more sort of yellowish. But this is not so instructive. So this is a nice way to do it. This is called the vector plot. And it's pretty, but it requires a bit of color. Stream plots give you a little bit more insight into what's going on, because the length of the arrow now scales with the region. No, it doesn't. But the arrow follows the stream. So this makes it clear that you're looking at circles, which is nice. So the color still tells you how strong the flow is. But here, like, you could be looking at a field which is a hexagon and some weird shape. It doesn't look quite right. Stream functions let us visualize fields that are going on. And that's incredibly helpful because you can start to think about the flux. If I draw this and ask for the flux around a circle, you know full well what the answer is. You don't have to do any calculations to figure that out. So stream plot is the best way to go. But look, there's some stuff about how to input them. The natural way to import to talk about vector fields is as vectors. So if you want to go do this yourself, read this bit about how to input it as a vector rather than as a list of scalars. Still works, nothing changes, but here I'm looking at f2 of xy. So I have a different vector field. My vector field is f2, which is just y, second element, and x. And you can see this is going to have divergence. Stuff is leaving, stuff is coming in. Will that be? No. Yeah, it will. Good. No, it won't. That's still divergence-free, but it doesn't exist at a point. Anyway, not interesting pictures. You want to generate, so here, I've got a function of a complex variable. Remember I said any function of a complex variable can be turned into a curl-free, divergence-free vector field by taking its real part and imaginary part. And that's exactly what is done here. So they take the real part, we take the imaginary part, and it gives us a field which looks quite complicated, but is overall 0 curl, 0 divergence. Okay, so these are good to know. Here there's a few more plots. So in this case, they're going to plot a much more complicated function of z. Fine. Let's look at its flow field. Kind of cool. You can generate as many of these as you want, and the fun thing is each of these corresponds to a 0 curl, 0 divergence vector field that can model, say, for example, electromagnetics or a flow, where any of these points where they sort of seem to converge or spread are points of sources or sinks. And you can even, because Mathematica is fun, look at what the real and imaginary part are. And if you wanted a challenge, you could probably try and construct f and g from those. I wouldn't recommend it, but it's something you could do if you have a spare 20 minutes. Okay. So you can visualize vector fields, and I promise you this is a useful tool to have in your back pocket. This is kind of the reason we put Mathematica here, is so that vector fields aren't just some abstract map that lives in your head. They are something that you can see. We treat them abstractly, but it is really important to remember that there is a concrete thing sitting at the bottom. It helps you sanity check, if nothing else. And then we talked about line integrals. So we have f3, and f3 is y, x minus x squared. And we're going to want to integrate it over this weird curve, t cos t divided by 2 pi, t sine t divided by 2 pi. And if we integrate it, as we covered last week, we can just ask Mathematica, what's the answer? And Mathematica is like, the answer is, you can do this, minus 0.528654. Done. Easy. For visualization purposes, we don't want to use that curve. We want to use the unit circle. So if we integrate that over the unit circle, we get minus 3 pi over 4. Let's actually look at it. So, because we integrated over a unit circle, we integrated over this circle here, and we got a number that's not 0, we know our field isn't conservative. There's no f. It's not a conservative field because we integrated around a closed curve and the answer we got was 0. If we kept integrating, we would keep getting more and more lots of minus 3 pi on 4. Fields that aren't conservative are difficult. Let's actually look at the original integration curve. So this is the first one we did. It integrated around that way, or possibly around that way, I don't remember. But we can start to visualize how our curves run through the vector fields. And with a little bit of cleverness, and you can poke through how this is done yourself, you can just look at the vectors along the curve. Remember, this is what you're integrating. The line integral along this curve is the projection of basically you project each one of these vectors onto the direction of the curve and you add them all up. The flux integral, perpendicular to the curve, let's say we can do that. You project all of these onto a normal direction that we'll define as outward, and you get that instead. So normal projections, tangential projections of the vector field. As we get very close to the origin, we can keep zooming in, and you can see that a lot of stuff changes very quickly, but you can keep doing that. And you can do the same thing for the circle, because we also did the circle integral. So this was the integral we did where we got minus 3 pi on 4 to convince us that it was not conservative. Yes? You kind of don't. Flux integrals, as I sort of mentioned before, are most naturally defined on curves that are closed. I don't immediately off the top of my head know if that definition actually extends to open, because it's not something you would ever think about. But if you just pick a direction and say, this is my normal, you can at least project onto that. So it is a valid operation. It may not be what we think of as a flux integral, though. That's what I got for you there. So we integrate around this circle. We only want these bits. So the vectors around the circle. Here, the field is acting tangential to the circle. Here, the field is acting perpendicular to the circle. So you can see how this is all going to work. And there's some more pictures where they just make things a little bit easier by projecting onto the normal. So here is the flux integral, which is just the amount of the vector acting perpendicular. Does it give us an answer? Yeah, minus 1 over 4. The rest is just calculations. It's not so interesting, but let's see if there's... Integrate the divergence. So you confirm that the same things are true. So here they plot the normal vector and the tangent vector, do some stuff. We're past the bit where I wanted to tell you. I wanted to get to this integral here. So turns out that you can look at how a vector field interacts with a curve, and you can start to sort of estimate what you might see. The thing you have to remember about Mathematica is it treats colors as size in vector fields, and that takes a little bit of getting used to. So for instance, the field is much stronger up here than it is down here. So look, visualize your vector fields. Visualize the way a field interacts with a curve and a surface. Do calculations. Convince yourself that Green's theorem holds. Next week, we will learn about the remaining major vector operations, vector identities, the divergence theorem and Stokes' theorem. And then we'll tie it all off together by talking a bit about what this means for fundamental theorems of calculus and Maxwell's decomposition. And then we're done vector calculus, so that's fun. Good job. I'll see you all next week.
Incredibly suspicious in the second half. This was fairly wide.
I've never had issues solving a differential equation in the it can't be that hard.
Trust your writing away. What are you up to now?
We actually cover a pretty significant amount of the 30th years.
Oh, that's good, because I'm not taking the third year piece. It is like method of characteristics solving by Fourier. Is there anything else?
Not really. Those are the two big ones we do in second year. Everything else is kind of fun.
Because like PDEs are generally not solvable. Like it's not like an ODE where there are the general.
We have to meet up sometime.
Yeah.
Have you watched the last episode of Free Room?
me a question. I don't care, but you've got to sort yourselves out. Free field and emergence free field. I'll see you next week. You're next.
Okay. I saw your email. If like I have some like ounce of time next week and I feel like doing the calculus and doing the quiz, can I do that anyway?
Yes, it's all.
If you got numbers, you use our number because you can do it.
It's a bit non-standard.
Not
Yeah.
Cool.
as if you
And I've already
for the Carson
Oh,
matrix.
okay. Great. The assignment is it like unlimited again, or is it also submitted?
So I need to work on that.
Because I'm done and I want to submit it, but it like freaks me out that if I like
Submit it, and then if you have a problem, email.
Okay, cool. Thank you.
So, I was wondering what the connection is between your work.
So I am very interested in what's called an asymptotic singular predicate. Now, what does that mean? Imagine a PD that as you, so ODEs, second order ODE, two linearly independent solutions, right? First order, one linearly independent solution. So if you have an ODE where there's a second derivative term and there's an epsilon, if I take the limit as that epsilon goes to 0, it goes from being second order to first order. Something really intrinsic to that ODE change. Singular perturbation is the study of where there are small or large parameters which how do you move between one? So my area of specialty is asymptotic. How do I rigorously do it? A lot of the optical setups they come up with can come up with what's called higher order dissipation. 4th order, 6th order, 10th order feeds.
Yes.
But the higher order bits have prefactors. My interest is if those prefactors are small. Say you have standard optics is the non-linear. Say we have 4th derivative, 4th order dispersion. Say it's very, very small. And we might say, look, this equation has an epsilon in front of the 4th derivative. Mostly looks like nice soliton pulse.
Yeah.
So if I put in just a tiny smidgen of 4th derivative, what actually changes? It turns out that tiny smidgen of 4th introduces oscillatory wave bands,
Because I was actually doing this last semester. We were trying to, we had a solver that used some sort of method, right? That if you plug in like some sort of input pulse, it converges to a solution.
Yeah. And I have a lot of really neat tricks.
So we're looking at, okay, what happens if you plug in any random dispersion relation?
Yeah.
Well, if you have, first you start off with quadratic dispersion, and then 99% quadratic, 1% quartic, and then that's exactly what we did.
So I have to work with my famous step.
Okay.
Yeah. This is so asymptotic analysis I teach in honest. It's pretty high level stuff. But instruments. I'm emailing my team. Stuff. But yeah, so asymptotic analysis are they? Because you can't just build around a solution when the perturbation is singular, because the equation changes. So it's how do I connect base solution second order with higher order dispersive 4th order? Oh, good question. Yeah. Okay, that's it. What are your names? Ramez?
Back.
Sorry?
Back.
We've exchanged
Yes,
emails.
we have.
Good to have you back.